Whatever happened to predictability? The milkman, the paperboy, the evening TV. You miss your old familiar friends, but waiting just around the bend.
In this series of videos, I want to talk about section 7.2 of Stewart's book, Trigonometric Integrals. We have two very concrete goals for this section. The first goal is going to be the focus of the first two videos, that is to integrate powers of sine times powers of cosine. The second goal, which we'll come back to in the later videos, is to integrate powers of secant times powers of tangent. So I'll start with an example that we already know how to do. Let's take the integral of sine to the fourth times cosine x dx. Well, one of the integration techniques that we already have is u substitution. And it turns out here, there's a very good choice. If you let u be equal to sine of x, then du equals cosine x dx. Why did I choose u equals sine of x? Because I have cosine x dx right here in the second part of the integral. So I picked u equals sine of x to make the du appear in the integral. So the integral that I'm taking is just the integral of u to the fourth du, which is 1/5 u to the fifth plus c. And our integral started with a function of x, so it should finish with a function of x. We substitute back, we get 1/5 sine to the fifth x plus c. Okay, this integral wasn't so bad because it's in a form where u substitution works really well. So let's do one more example. Let's take the integral of cosine to the fourth x times sine cubed x dx. This one is a little trickier. One way to think about it is this integral is equal to the integral of cosine to the fourth times sine squared x times sine x dx. Okay, this is true. It's not totally clear why you would want to write it this way. But the idea is now we have a sine x dx, which is almost equal to du if u is equal to cosine x. So if u equals cosine x, du is negative sine x dx. With this substitution, we have the integral of u to the fourth times sine squared x, which we'll come back to, times -1 du. And usually, this is a very big problem, that we have a u to the fourth times sine squared x times -1 du. Because remember, we never want to mix x's and u's. So this is only going to work out if we have some way of rewriting sine squared x in terms of u. So I'll pause and erase, and we'll see how to deal with this problem. So the big idea that's going to make this integral work is that we can rewrite sine squared x equals 1 minus cosine squared x. Why is that true? Why does this work? Well, sine squared x plus cosine squared x equals 1. If you know one trig identity, that's it. How does that help us? Well, in this case, we have sine squared x equals 1 minus cosine squared x, which is equal to 1 minus u squared. So the integral that we're working with, u to the fourth sine squared x times -1 du, let me pull out the -1 du, we can write as minus integral of u to the fourth times 1 minus u squared du. And this integral we can do by expanding. This is minus integral u to the fourth du plus the integral of u to the 6th du, which is minus 1/5 u to the 5th plus 1/7 u to the 7th plus c. And we started with a function of x, so we should finish with a function of x, substituting back minus 1/5 cosine to the 5th x plus 1/7 cosine to the 7th x plus c. So what was the common thing in both of the examples? The main idea was we isolated a factor of either sine or cosine with the dx, and then we applied u substitution. And then apply u substitution. In the first case, we could apply u substitution right away. In the second case, we had to first use this identity, sine squared equals 1 minus cosine squared, which comes from sine squared plus cosine squared equals 1, before we were able to rewrite our integral entirely in terms of u. So how does this idea generalize? Well, if you can rewrite sine squared as 1 minus cosine squared, then sine to the 2nth power is sine squared x to the nth power, which is 1 minus cosine squared x to the nth power. Similarly, cosine to the 2n x is equal to 1 minus sine squared x to the nth power. So what does that mean? That means that we can rewrite any even power of sine just in terms of cosine. For example, what is sine to the 4th x? This is 1 minus cosine squared x squared, which is 1 minus 2 cosine squared x plus cosine to the 4th x. So if you have an integral that has an even power of sine, you can rewrite it entirely in terms of cosine. This will be very helpful when we want to apply u substitution and take an integral that's entirely in terms of x and write it entirely in terms of u. Same idea, if you have an even power of cosine, like cosine to the 6th, then we can rewrite it as just involving sine. So in the next video, we'll see how to use this idea to solve a very, very large class of integrals of the form sine to a power times cosine to a power.